Welcome to our webinar this evening on renovating 33A Chapel Street in Appleby. I'm Tina Holt and I'll be talking to James Innerdale, Chris Morfitt, Penny Randell and Ilias Igoumenidis, who are our panel for this evening. So after a few words from me by way of introduction, the presentations will start. We've got two main presentations from James and from Ilias, with a few words from Chris and Penny as well. Then at around about 10 to 7, we'll go on to the Q&A, where all of our panelists will be able to answer the questions that you put to us. And at the end, I'll have another poll and a couple of next events, aiming to close on time at 7:30. So for those of you who aren't aware of Cumbria Action for Sustainability, we do a lot of other things, not just talk about webinars on retrofit. So instead of going through this slide over and over again in every presentation that I've been doing recently, I would just encourage you to go to the CAFS website and find out about all the different things that we do as CAFS and all the different projects that are currently running. Within the Energy Services team, which is the team that I work in, we have some projects that we're running for free and services that we run for free, and others that are paid for services. So on the free side, we've got Cold to Cozy Homes, our energy advice service, phone calls and sometimes visits, and sometimes draft proofing for people who qualify. Also, which might be useful for some of you on this webinar, we offer short general advice phone calls on a specific question. That might be a particular kind of insulation or solar panels, something like that. And we also have a free 30-minute retrofit consultation by phone. So if those things might be useful for you, keep that in mind. On our paid for services side, we have our energy advice audits, and that we use a product called Home Retrofit Planner for a whole house scenario. That, of course, is paid for, as is our thermal imaging service. And these webinars, we run courses and webinars, and sometimes they're free, sometimes they're paid for. This one's free, thanks to the energy redress funding that we have. But thank you very much to those of you who have put in a donation, because that always helps CAFS do more than it would otherwise be able to do. So, moving on to the panel then. So I'm going to start by talking to Chris from Lake District Lime, who did most of the work on the house at Chapel Street, and then I'll introduce James and finally Penny and Ilias. Now I can see someone's raised their hand. I just wondered if it's a technical problem. Perhaps we could just check whether there's any difficulty from anyone with hearing this webinar. If you could pop a question into the chat if there's an issue, then just let me know and I'll try and answer it while the talks are going on. So Chris, I would like to start by asking you a first question. So in terms of the timeline, what was your, when did you start? When did you finish? What were the key steps?
Yeah, so the property was purchased in early 2018. From there, moving forward, we obviously had to get in touch with planning. There was conservation, there was building regs. The property was formerly commercial. It was a charity shop, if anyone knows the area. So we had to change that to residential, give it a name. So there was a process there that took about 12 weeks in total. The property is in a flood zone. It's a grade 2 listed building. It was built in the early 1800s. It's traditionally built with a local red sandstone, which warranted some works that I perform, and I was keen to open the property up to the public. And it just so happened that there was a heritage action zone that was showing interest, along with yourselves and Historic England. So it became a project where I could open that up. It had been slightly mistreated with hard cements, things like that. So it was stripping everything back to bare stone. That was when Historic England were involved, putting in the wooden dowels and the monitors and the sensors. so we can see how the building performs. We repaired the roof structure. We slated with a local slate. We used wood fibre boards in the insulation. We rewired the whole property. It has a problem from historical flooding, so everything was brought above flood level and the fuse boards were moved higher. So there's not only flood resilience, it's all year round function as well with the lime, which leads me on to, we plastered downstairs with a putty, a middle floor with a cork-based lime render, and a top floor with a hemp and lime render, for personal interest to see how those performed. We also put Limecrete floors in, underfloor heating, lime harled outside, so there was all the renders to be removed from hard cements again and changed them back to lime renders as they were originally, and new rainwater goods. So all the important bits, really, the maintenance of old properties, as well as retrofitting for insulation values and to help with energy. So we completed November 2019.
Brilliant, brilliant. And so that's November 2019 to now. That's got 2 and a bit years. So the occupants, how are they finding it living in this newly renovated property?
Yeah, they're cozy was the word they said. We've got insulation right around the walls. We've got underfloor heating. We used wood wool board on the stud-works, and we've got sheep's wool insulation within that. So they're really happy. I'm really happy with how it's performed and looking, and hopefully the data that we see coming back from Historic England will wrap that up as well. Yeah.
Brilliant. Well, thank you so much, Chris. So that's wonderful. It's a lovely introduction to it. So I'm going to now hand over to James Innerdale. And James has been the architect who's done all the work associated with this project. And so James can give us a full picture of how you started that and what choices you made and why.
Right. Thank you, Tina. I'll just attempt to share my screen. Bear with me a minute. We'll do this. Can you see that?
Yes, that's
Good.
Brilliant. Thank you.
Lovely. Thank you. Right. A little bit of what I'm going to say is sort of repeat what Chris has already said, but with some pictures as well. I was asked to be involved as an architect. I'm a conservation architect, work with historic buildings most of the time. And Chapel Street's a really interesting project in that there was it's a combination of looking to improve the energy efficiency of the building, but at the same time looking at the fact that actually it also needs to deal with issues of flood, so flood resilience, and frankly not just flooding, but as we've experienced this winter, just more extreme weather, more of the driving wind and the rain that the building has to cope with. So that image is thanks to Ilyas from their website of it in its very nearly completed guise with a new lime render on the outside. This is it in its early days, as Chris said. It's a red sandstone rubble building. You can see the building next door to it is a dressed red sandstone property, but this one is rubble stonework, so it's sort of it's rough rubble, but it's rubble stonework with a originally a lime hull or lime thrown render on the outside and dressed sandstone surrounds to the coins in the corners and the windows and the doors. But that has been was variously repaired or repainted in impermeable, sort of breathable paints on the outside, and the back wall was also re-rendered, as you can see on the right-hand image there, in a cementitious, hard cementitious render, and there are various cement repairs done to the render on the front as well. That's a shot around the side on the left-hand side. You can see, if you can see my mouse, this is actually the original lime render here, but then it's been variously patched and painted in various bits and pieces, and you can see the damage that the not regular flooding, but the flooding has caused as a result of the fact that the water has been trapped within the wall and blown the render off and caused various bits and pieces. And round the back, this is the back wall, and then there is a courtyard with a few outbuilding buildings attached to it. And we'll come back to this later, but when it did flood, water both came in from the front and also at the back into this courtyard as well. The bottom image is a view looking out, going out towards the rear courtyard of the property. So here's not very clear images at all, but sections and plans through. So it's on 3 floors, ground, first and second. Here's a sort of cross section through it. Well, this shows it, this right hand image shows it better. So you've got the street to the right hand side and the courtyard to the left hand side with the 3 outbuildings that you can see there. And this is a view of the roof, showing on the right hand side 33A Chapel Street, and to the left hand side the roof to 33 Chapel Street, the dressed red sandstone building that you saw on the first image as well. Things to note here, just out of interest: a redundant chimney at the back here, which going forward was proved to be problems, but had obviously over the years got extremely wet and yeah, reacted slightly differently to the work that was carried out. So when you're thinking about, I'm sure a lot of you will be aware of this, but when you're as part of this exercise, one of the crucial things when you're thinking about retrofitting a building, be it a new one or an older one, and we're talking about a traditional building here, you need to understand how the building is constructed, because you need to understand the implications of the retrofitting, what you're doing, what are the implications of that on the actual physical performance of the building fabric, how it actually deals with moisture. And clearly, as you saw from the pictures I just showed of the building before the work started, what they had been doing was such that the building wasn't happy, it wasn't dealing with the moisture in the way that it should be. So traditional solid, it's like Chapel Street, it's a traditional solid wall building like this on the left hand side. It's 2 skins of masonry rubble stonework with some loose fill in the middle, built using lime mortar, and the stonework itself is also lime mortar is porous and permeable, as is the stonework itself. The principle is such that when it rains, the wall absorbs the moisture, and when it stops raining, that moisture is allowed to evaporate out again. The idea of breathing, which I'm sure you're all very familiar with. And in the case of Chapel Street at Appleby, there was also a layer of lime render historically on the outside, which would have aided that drying process. And historically, it would also have had a lime plaster on the inside that would have aided the drying process to a degree to the inside as well. But all of that had been compromised over the years by the use of inappropriate materials, non-breathable, impermeable, non-porous materials that are more akin to the image on the right, which is of a modern cavity wall construction, which works on the basis of stopping water getting into the building in the first place. So it's using a lot of, as I said, impermeable, non-porous materials, so cementitious-based materials. So you might, for instance, put a cement-based render on the outside of a cavity wall, and whilst it maintains its integrity, that's fine. But if it cracks, water might get through those cracks, might get through the outer skin of the cavity wall, but when it gets to the cavity, it can run down the cavity and come out of weep holes at the bottom of the cavity. So there are layers stopping water getting into the building. And as 2 forms of construction, they both work independently fine. The trouble is when you actually combine the 2. So if you take, as they did at Chapel Street, that cementitious render and put it on a traditional breathing solid wall construction, by doing that, you are putting should we say, an impervious membrane on the outside. And whilst it maintains its integrity and stops the water getting into the building, that's fine. But if it cracks, which it inevitably will, and water gets through those cracks and into the core of the wall, by putting that layer on the outside, you stop the wall from being able to evaporate the moisture out, and the water gets trapped within the wall, and you get problems with dampness inside. And as at Chapel Street, you also get the start of problems with erosion of the stonework as well. In a wee bit more detail, the lime, crucially, the lime mortar with which is built is or should be of equal or greater porosity than the actual stonework itself, on the basis that most of the evaporation of the moisture that I'm talking about in the breathing happens through the lime mortar joint. So if you replace that with something that is less porous, less permeable than the stonework, the evaporation of the moisture then occurs through the most porous element of the building, which is now the stone or the brick. And when it does that, it brings with it salts, which then crystallize on the external surface of the stonework and cause erosion of the stonework. On the right-hand side, two examples here. This is a very exaggerated version, but this is a red sandstone building which has been very, very heavily pointed in a cementitious mortar. And that erosion that you're looking at there is principally as a result of the fact that they've used a cement-based mortar rather than the lime-based mortar. But similar things were happening at Chapel Street as well. At the bottom, on the front, you can see there was increased erosion of the red sandstone dressings at the base of the door, and that was because the building was flooded, water is being absorbed by the wall, and the most porous element of the building now is the red sandstone surrounds the doors and windows. So the water was coming out there and causing increased erosion to those sandstone elements of the building and causing the building discomfort at the same time. And from the context of retrofitting and adding insulation, you need to bear in mind that process of breathability, and bear in mind that that process of breathability also requires a degree of warmth in the wall to allow the evaporation process to occur. So you need to think about, if you're introducing insulation into your building, what impact is that going to have on the performance of the wall in terms of the evaporation of the moisture, allowing the moisture to dry out. This sort of graph on the left hand side shows you the sort of, got the inside on the left with the warmth from inside coming in, helping with the drying process. So if your options are, if you insulate to the external face, which you can do, there are, and I know Ilyas afterwards will talk about different types of insulation, but you can insulate externally. If you do that, it has the advantage that you're using the mass of the wall to hold the heat from the house, so the wall acts as a heat store. However, if that insulation that you use on the outside is not breathable, you are in essence putting a cementitious type render on the outside and trapping any moisture that gets past it in the wall, which is a bad thing. There are breathable forms of external insulation, and certainly in the right situation they have their place, but obviously external insulation has the other issue with the fact that it has a significant impact on the external appearance of the building around doors and windows and eaves. So your other option, if you're not going to insulate on the outside, is to insulate on the inside. And if you do that, the implication of that is that less warmth from inside the building is getting into the wall. And you need to think about what happened, what the implication of that is on the drying process. And that's actually quite important. Because as part and part, in addition to the heat that you're getting, or the warmth that you're getting from inside the house, there is also moisture vapor from us generally living, our general living process, just being in the property, and we're producing moisture vapor, and that also travels into the wall as well. And with your sort of impervious type, impermeable insulations like foam boards, without naming any particular product, but insulated foam boards, the cheaper insulated foam boards, they're cheaper, but they're not breathable. And in theory, they should come with a vapor control layer, which stops that vapor from traveling through the insulation into the wall. But more often than not, they're not very well fitted, and that doesn't actually happen. And that's an issue, because if that vapor gets past the insulation and hits the wall, that wall is now colder than it was before, and there is potential with issues of condensation and actual physical, rather than moisture in vapor, form moisture, it becomes moisture in liquid form, so what we refer to as interstitial condensation. However, if you use a form of insulation that is breathable, like we have at Chapel Street, then that is not really, well, it's certainly significantly less of an issue, because the vapor that transfers through the insulation into the wall can equally be transferred back out again, and you have much less in the way of issues with regard to condensation within the wall. Another thought to comment to make on the basis that Chapel Street, we're looking at issues related to it's not just retrofit, it's also flood resilience as well. In both instances, before you start any of this exercise, make sure your building is weather tight in the first place. Deal with those problems that you haven't dealt with for a while before you start going down the line of retrofitting. Make sure your gutters and downpipes are actually functioning properly, not like this building on the left hand side with the ferns growing out of the hidden gutter. But you can I don't know whether you can see, but there's also an area of below those ferns, an area of slightly darker brickwork. So that's obviously been happening for some time, and that's an area of the wall which is probably holding a lot of water. So make sure your building is weather tight, make sure your gutters are working well. Maintenance is key in this respect. And if you're going to go down that line, if you're going to check your gutters and your downpipes, go and do it on a rainy day like we've been having recently, because the building will show you where the problems are, where the water is spilling over the gutter. This image on the bottom right, it's clearly evident that there's a problem there with the gutter. You might not have seen that on a dry day. So go out and have a look on a rainy day or immediately after a rainy day. And it's not just the gutters, it's the downpipes as well, where they come down. And if you can't do it on a wet day, there are quite often clues in terms of the outside of the building. You might get staining if your building is a brick building, or actually come to that, a stone building. What you're looking at here, this white staining on the wall here, is efflorescence, which is salts which I talked about before, being drawn out from the wall. And that's an indicator that further up that downpipe is a leak, and water is being discharged into that wall and actually soaking that wall. And that's something that you would need to attend to. And similarly, when you get to the bottom of your downpipes, make sure the gullies and the drains and everything is working from the point of view of actually taking that water away from the building. Rainwater goods are key in that respect. And particularly also have a look at your roof as well. Make sure the roof is working, particularly after the endless storms we're having this winter. Check the condition of the roof, make sure the slates have not slipped or broken or missing, and also check the flashings where the roof, on the right hand side, where the roof abuts any wall or chimney, to make sure there are no cracks or failures in there. Usually that flashing is a lead flashing, but it might be, as in that image, a mortar-based flashing, which might be a hard mortar and they tend to crack over time, and water can drive in there and get into the body of the wall. So those are all things that you need to keep an eye on as part and parcel of checking. So it's diagnosis, visual clues. The building will show you where the water, I put this up, it's perhaps not directly relevant, but it was a classic situation of a building where they'd had problems on the left-hand side with dampness over the years, and they just kept coming back and replastering it in a modern cement, gypsum-based plaster, and it was still coming back. And they hadn't actually addressed the issue of where's it coming from. And if you went outside, the right-hand image is the outside image, and you can see we've got a blocked parapet gutter and a hopper which isn't connected to the downpipe. And all of this problem inside is a result of the lack of maintenance outside. So that's important. And when you're thinking about flood resilience, also we've been talking about lime from the point of breathability. That's also important from the point of view of flood resilience as well, because a lot of the materials used in traditionally constructed buildings are, as I said, are porous and breathable, and a lot of them can stay in situ because they absorb moisture, but equally they allow it to evaporate out again. So there isn't necessarily, after a flood, a need to strip out and replaster and lose all all of those materials as part and parcel of that process. And in terms of flood resilience, the other key element to think about in terms of if you're in a flooded area that has potential for flooding is, where is the water actually coming from? And that is key. For instance, there is no point in putting a floodgate on the outside of your building if actually your building is going to be flooded as a result of groundwater coming up through the floor. So it's important to bet, is it at Chapel Street, most of the water was coming down the street and coming in the back door and the front door. It had a concrete floor, so there's probably, in addition to that, there was probably likely to be water when it flooded coming up from the ground below as well. But it's important to bear in mind, think about where is the water coming from, and that will perhaps help you make a decision in terms of what measures you should be undertaking from the point of view of actually flood resilience and flood resistance measures. And also important to bear in mind, actually, if you're in a terrace or a semi-detached property, what are the implications going to be of the work that you're actually carrying out? For instance, going right to left here, and if the water is coming down off the fell, perhaps, if you put in a concrete floor in your building as part of your retrofit measures, that's going to stop any water. It might stop the water rising up through the floor, but it's going to push, as Chris talked about before, push the water to the base of the outside walls, and the water may come up the base of the outside walls and show itself as rising damp at the base of the walls, but also it might transfer that water across into the next door property and increase their issues. So you need to think about what's happening with your next door neighbours. In terms of flood resilience and flood resistance measures, at Chapel Street it was a combination of the two, and with a lot of traditionally constructed buildings, that's what it's going to be. It's using breathable, permeable materials that, whilst they might get wet, will be allowed, can dry out again and be left in situ without necessarily having to be stripped out. That in combination with flood resistance measures, which basically means measures that stop water getting into your building in the first place. And whilst at Chapel Street they've not completely been carried out for various reasons, the idea was to introduce flood gates on the front and the back to stop the water coming in the front and the back in the first place. And also potentially there is a manhole immediately inside the front door of Chapel Street, and to put in a non-return valve in that manhole to stop any contaminated backflow water coming from the sewers, sort of backflowing back into the house. So putting sort of return valves in the manhole there. And also we discussed the idea of putting in a sump pump in that front entrance area as well. Idea of a sump pump. A sump pump is set into the floor, and it basically, as soon as the water gets to a certain level, it starts pumping the water out of the property. And that's very useful to keep your building dry for a period of time, to enable you to move. If you've got precious objects and bits of furniture at lower level, you can move them, gives you time to move them away to upper levels before if the water continues to rise outside. That image on the left is an example of a building in Staveley where they had exactly that. They had a sump pump inside that pumped the water, kept the water at bay, and gave them enough time to move things out. It didn't stop it coming in eventually, but at least it gave them time. And Chris has already mentioned the services, making sure services are in the right location, not within the flood zone, having your boiler at first floor, making sure all the services are coming down from above rather than up from below as well. So moving on to what was actually done at Chapel Street, I mentioned the flood resilience measures. In terms of the retrofit, as Chris has already said, at ground floor, the existing concrete floor was broken up and it was replaced by another solid floor, but it's a breathable solid floor, a limecrete floor, and that's what you can see going in there on the right hand side. So that's recycled foam glass being laid as a base layer, and then a lime screed being laid on top of that with underfloor heating within that. The idea of that is that, again, if the building floods, that doesn't have to be stripped out. It can dry out over time and enable you to continue to, ideally, not necessarily, may have to leave the building for a short while, but at least get back into the building fairly promptly afterwards. And then at ground floor, there was the issue that, and this is maybe something we can discuss later, that regrettably quite a lot of the insulation products that are appropriate for traditionally constructed buildings, breathable forms of insulation products, don't cope very well with standing in water for a long period of time. So at ground floor at Chapel Street, took the decision that actually we would not insulate the walls at ground level below the anticipated flood line. So as you can see on that image there, I think it's about 1.5 meters, Chris, something like that. It's just insulated in lime. It's not insulated at all. It's just 3-coat lime plaster, and then above that is an insulating lime plaster up to the underside of the ceiling. So we've accepted the fact that actually it's better to avoid having to strip out in the area of the flood zone if it does get flooded than to insulate. So you may feel that actually you'd go the other way and actually accept the fact that there's going to be a zone there that you're going to have to replace every time it floods, or as here we took the view that actually from the point of view of disturbance of the building, it's better to not insulate that lower section so the occupants can actually stay in the property as long as possible. And then on the upper floors, as Chris has already said, at first floor, which is this image here, it's the cork-based diaphalite insulating plaster that Ilias will talk about in due course. And then at second floor is Eden's hemp lime insulating plaster. And interestingly, you'll see a difference in thickness there. At first floor, it's only, in essence, 20 mils worth of plaster as a preference to, at second floor, you're actually looking at just over 50 mil worth of plaster. That's because of the difference in thermal conductivity of the two materials. So they're looking to, what we looked for here was to actually, so they both achieve the same U value, so they both achieve the same thermal performance in terms of the wall. So when we were monitoring it, we would get an idea of actually, so it was, if you like, a level playing field for both floors. So that meant that there was a much thicker amount of insulation at second floor than at first floor, because the hemp lime plaster is less good as an insulant as is not as good as an insulating plaster as the diaphanite. Chris also mentioned the wood wall boards on the partitions within the property. That bottom right hand corner shows you the wood wall boards before they were plastered. And on the roof, after it was reslated, well, before it was reslated, it had, so there was a slate, and then there was battens and counter battens, and then there was a breathable roofing membrane, and then there was 20 mil of wood fiber board as a sarking board, and then there was wood wall bats, flexible wood wall bats between the rafters, and then to the underside of the rafter there was then a further 60 mils worth of wood fiber board, which was then skimmed on the underside with a lime skim. So that was the build up. And as part and parcel of this whole process, Historic England introduced monitors into the building, so we could actually see how these improvements actually performed in reality, rather than as a desk-based exercise. These images are prior to the works being done. They sort of did some monitoring to see how the existing walls and floors performed in terms of moisture content and relative humidity and their U value. And various monitors were put in various locations. This one shows, well, there were monitors, there were dowels, a wooden dowel and some porcelain dowels put in to measure moisture content. There were also measurements for relative humidity and temperature as well, generally all in the same sort of locations, number of locations around the building on ground floor, first floor and second floor. And whilst all this data is not fully collected and put together, it has come up with some quite interesting bits of information. So this shows you so there's a wooden dowel that gives you an accurate measurement of the moisture content. So here's your wall and dowel within the wall, which then has its moisture content measured. And then there are, as I said, relative humidity and temperature sensors at the junction between the plaster coat and the masonry coat. And the point of locating them there is because this, if you go think about my previous slide, this is if you're going to get issues with condensation within the wall, that is the zone where it's going to happen. So that's partly why that monitor is located in that particular location. Also took some, these were taken in 2020, Chris, I think, or 2019. Yeah, thermal imaging cameras. So these are images of the building after the work has been completed. So you can see clearly at ground floor, the fact that you've got a greener, yellower, red zone. So there's more heat being lost at ground floor because we haven't introduced insulation within the plaster at ground floor. So you can see that heat is being lost there, but you can see the benefits of the insulation to the walls at first and second floor, particularly when you compare them to the property next door, which hasn't had any retrofit work done to it. A few more images here. This is in the ground. When you come in the front door, this is the lobby, and you can see how cold it is here, partly to do with the fact that it's adjoining the next door property, but also partly the fact that we haven't actually insulated a ground floor, and also this area was not didn't have the limecrete floor introduced into it. But you can see as you go up the wall, the color of the bands change as you go up, as the actual improvement to the thermal performance of the walls can be seen by those bands. Some other similar shots, ground floor. This is ground floor looking towards the street with the gable end to the left-hand side as you're looking at it. So you can see the if you like, the jade blue of the zone where it wasn't insulated, and then you get into the zone where you're starting getting insulation similarly there. And then on the right-hand side, we have an image at second floor, looking towards the back wall, and you can see how well it's performing from the point of view of retaining the heat, other than this area in the corner here, which is still quite blue. And I mentioned earlier that chimney at the back of the building, which was very damp, and obviously that is continuing to not present a problem, but that area is still particularly damp, and it's going to take a while, a little bit longer to settle down in that particular area. But thermal imaging cameras are really useful in this respect, in that they can show you where there are potentially ongoing issues. And just also, we've got some information back from the data, which is quite interesting. It's 2021, and you can see this top graph is the moisture content at ground floor, and you can see that it's generally going down. A couple of the ones from ground floor, front elevation and gable elevation, you can see the moisture content generally dropping, which is what you would expect it to be doing. I'm just having a reminding myself. So yeah, on the gable, it's dropped. That's the one that's noticeably dropping at ground floor. I put this one in as a little quirk. that generally it seems to be fairly good, and then you get this sudden spike in moisture content. And it's interesting that these sort of monitors identify these things. And I asked Chris about this, and Chris said this is the wall. It says north return. This is the wall that is next to the adjoining property number 33, and they had problems with their roof and water leaking from their roof, and obviously water was getting into the wall of number 33 as well, which was called 33A, which is causing this spike. So as an exercise, it's very useful. It shows you it's got wet, but then it's settling down and beginning to dry out again. Then there's also relative humidity sensors as well. One at ground floor, again, dropping. There's a little bit of spikes over time. It sort of goes up a little bit on the basis that relative humidity is in part related to temperature as well. You get little spikes when the weather gets colder here. I was puzzled by this, however. This is at first floor. This is the bathroom here. I was thinking, what's going on here? These are very up and down in. This is just me looking at them and thinking about them, but I'm thinking, is it to do with the fact that this is a bathroom and this wall is actually having to, you're getting these sort of, they're not staying high, they're up and down and up and down, and they are related to the fact that the walls are absorbing the high levels of moisture vapor from the bathroom when the bathroom is being used, and then allowing that moisture to evaporate back out again once the bathroom stops being used. So those spikes relate to the fact that the wall is being used as a bathroom, and it actually shows that to a point that the lime plaster is actually doing what it should be doing. And finally, just some interesting graphs in terms of rainfall, and to make the point that actually when you're looking at your building, not all elevations are going to be the same. Different elevations are going to get different hits in terms of weather. So this top one is rainfall across each elevation, and you can see that the gable elevation is the one that gets the brown orangey one, gets the most significant amount of generally most amount of rainfall over time, and that, depending on where you are, that might change and or inform what you do in terms of your retrofit and your approach to actually dealing with the building. And similarly, I don't know whether you can see them clearly at the bottom, but you've also got different this is to do with the sun and solar, and obviously the front and the side are doing get more in the way of sun than the rear, and that potentially is that's going to be important from the point of view of the sun and the heat do have an impact in terms of the ability of traditional walls to evaporate that moisture out, and it's something that you need to bear in mind as well. I have overrun a wee bit there, but I hope.
Thank you, James. That's been really interesting. Seeing the data as well as the photographs, and actually seeing what's happened since the end of the work was really, really interesting for me. So without further ado, I'm going to invite Penny and Ilias from Ecological Building Systems to talk about the products that were used in Chapel Street. So I'll say over to you.
Right, thank you very much, Tina, and thank you very much to CAFS for inviting us along this evening. We've had a very long-standing relationship with CAFS over many years. So very briefly, an introduction to Ecological Building Systems. We actually set up in the county nearly 14 years ago, and actually started in this room that I'm in at home, and gradually over the years we've now got extensive warehousing, offices, and a wonderful team of people based, as I say, at Dalston near Carlisle. Basically we supply natural insulations and airtightness products, and some of those products are Gutex, which is a wood fibre insulation. We do Calcitherm, which is a calcium silicate board. We do a flexible insulation called Thermo Hemp Combi Jute, which is a mixture of both hemp and actually recycled jute bag fibres. And as well as that, the Dyson range, which Ilias is going to be talking about today, and which was used on Chapel Street, which is a cork lime thermal plaster. And we also do a range called Proclima, which is airtightness and wind tightness membranes, tapes and seals for both retrofit and new build. And we're so fortunate that over this period we've worked on so many low energy and passive house buildings, along with retrofits throughout the UK and Ireland, and we've worked with some fabulous people, and we're delighted to be involved with Appleby and Chapel Street and Chris and James on the project. So I'm going to hand over to Ilyas. Ilyas has been with our technical team for over 5 years. He's an engineer, a passive house designer, a passive house contractor, and is absolutely wonderful on retrofits. I'll hand you over to Ilyas and look forward to your questions after. Thank you.
Thank you, Penny. So I'll just go quickly. Yeah, so my presentation is going to be short and sweet. Thanks, James, for that was brilliant. I mean, in such a small period of like 20 minutes or 25 minutes, you've break down so well all the problems more likely that everyone's going to meet when retrofitting, especially that types of buildings that are so challenging, solid wall buildings. Now, what I've done is that I tried to collate, to make a diagram showing the strategies very briefly and the benefits and the risks when retrofitting. And then I'll show you again a breakdown of some systems, the most common systems we suggest for especially that type of buildings, solid wall buildings insulated internally. I'll just go quickly and start. That's so basically that's the challenge of retrofitting, and that's the main objectives. These are the main objectives we try to meet. First, reduce the thermal losses, of course, through the fabric. Second, minimize the condensation risk. And third, improve the indoor air quality. And all these objectives are somehow interconnected, so that's very important. And for achieving that, what we do is we try to implement some strategies and take some measures. Passive House Institute talks about 5 main principles that we use for new builds and for retrofits, but that applies across the board, and no matter if it's passive house or not a passive house, these measures should be followed. And again, these are again interconnected, and I'll go through them one by one. So first of all, of course, is insulation. So we insulate the house and we try to minimize the thermal losses through the improvement of the fabric. We do that by trying to improve, or at least not make the thermal bridges worse. Thermal bridges are all the cold spots, and very brilliantly the pictures from thermal imaging James showed earlier show all the imbalances in the fabric when you insulate some parts of it and some parts of the fabric are not insulated. And that's the challenge, especially in retrofits. You cannot do the best every time. The third principle is replacing the windows if possible. Again, in traditional buildings or in listed buildings, that may be a challenge. You may not be allowed to do that. But again, that's one of the challenges. The fourth is airtightness. We try to improve the tightness of the buildings to eliminate the uncontrolled air leakage through gaps and cracks and along the window reveals, for example. And lastly, when we do all that, we should somehow incorporate a ventilating strategy in our design, because that's gonna tie up the whole thing. Now, the placement of the green boxes is not random because I'm sloppy. It's for a reason. I'm gonna start interconnecting now all these boxes, and you'll see why is that. So there are some benefits from each green box and some side effects, some risks that may be incorporated in implementing on each one of these strategies. So by insulating the building, of course, we improve the fabric, we reduce the thermal losses, right? But at the same time, depending on how much insulation we add and where is the exact placement of the insulation. James said before, it's different if you put the insulation on the outside in comparison to putting that on the inside. If you put the insulation on the outside, then you create a warm jacket, a warm building, so everything is included and the condensation risk is minimized because you have a warm skin of the building. However, if you do that, which is in most of the cases what's happening in solid wall traditional or listed buildings, if you put the insulation on the inside, then the actual skin of the building becomes colder, and then that's where interstitial condensation may occur. So that's a side effect of the insulation. And also, again, if you don't insulate everything smoothly and continuously, if you leave the window reveals uninsulated, or the intermediate floor junctions, or the shutter boxes, or any places where you cannot add insulation there, these could be side effects, and this would create thermal breaches and potentially moisture risk. And whenever you insulate your building, either you design it or not, you are going to improve the tightness of the building, and that may be good or bad thing. So maybe a bad thing, because when you improve the tightness of the building, then you have everything enclosed and you may suffocate in there. There's no fresh air coming in, or moisture like humidity getting out, so there's no refreshment, and that may be a problem. But on the other hand, by improving their tightness, of course, you reduce the thermal losses because you control the volume of air, and there's no uncontrolled escape of energy through the leakages. But for their tightness to be a success, this needs to be incorporated with ventilation, any sort of ventilation, either natural ventilation or even better mechanical ventilation, more controlled and more well-designed form of ventilation, because that's going to improve their indoor air quality by introducing a new, fresh, filtered air into the building and minimizing the condensation risk, because that's going to reduce and regulate the relative humidity and the vapor that is produced by our activities in the house. And of course, if you use ventilation with heat recovery, mechanical ventilation with heat recovery, this could also be beneficial from the thermal loss point of view, because the control air that's getting out and it's getting in the house is preheated. So again, you have a benefit by recovering some sort of energy through that process. And there are some side effects on the ventilation. If it's not well commissioned, you may have a very dry air if it's not well commissioned, but that's not for today. Let's go back to the tightness. So windows, again, replacing the windows will improve their tightness if installed properly with all the airtight tapes around the frame, and will reduce also the thermal losses, because it's going to be better glazing, like double glazing or triple glazing even, and a better frame with a better U value. But if not installed properly, then this again will create probably thermal breaching. So by placing the windows on the inner side or the other side, the outer side of the wall may play a huge role in the thermal breaching effect. And of course, thermal breaches themselves are a side effect themselves, so they create thermal loss, they increase the thermal losses, and they create condensation risk. So that's a spaghetti thing, and actually that's actually how we should think when we go and retrofit. Instead of taking one of the boxes, we should think in combination, and I think all the side effects, and eliminate the side effects if possible. So the only way to do that is to have a whole house strategy, because otherwise we may create more problems than solving. So that's how we should do that. And to do that, of course, we need three things. We need a good designer, we need appropriate materials, and we need proper installation. So we have James here, we have Chris here, and guess what? We are here to go through some materials. Yeah, you might have heard James talking about vapor open or breathable construction, hygroscopic. Another term that's usually used is capillary active, and of course airtight. All these, okay, it's too tight of the time today to go through all that, but just as terminology, you'll come across all these words. Now I'll go through some systems for the walls, roofs, and the floors. So first of all, for the walls, I mean, there are lots of systems out in the market that are advertised for using for internal wall insulation. But yeah, as James said, we should be very cautious. We should be using vapor open materials. We shouldn't be leaving any gaps between the actual skin of the building and the insulation, because this gap is going to create a huge risk because it's high humidity on a cold surface behind the insulation, and this humidity should be somehow regulated, and if it's not fully bonded to the insulation, then it's difficult to evaporate. So all these systems I'm going to introduce to you today are going to be fully bonded to the stone or the brick, right? So first of all, diaphanite, which also has been used in Appleby, in Chapel Street. So diaphanite is a range of plasters and screeds, lime-based products, vapor open, and very capillary active. And by saying capillary active, we mean they can actually actively pull the moisture off the wall and evaporate it to the inside. So they're not only breathable in the sense of they allow the moisture to pass through, but they also assist the moisture actively to be transferred to the inside. So all natural materials are hygroscopic, and they allow the moisture, they temporarily absorb the moisture and release it back. But especially diaphanite is also capillary active to activate that movement. So diaphanite is lime, essentially with a huge amount of tiny core granules, up to 3-4 millimeters. It can be applied very easily, either by hand or sprayed through a machine. It can be applied in layers, 20-25 millimeters per layer. There's no, I mean, as long as the wall is clean and stable, there's no too much preparation. You can just apply the material onto the wall. You shouldn't be pushing material too much, because you don't want to push the air out of the material. You can see on the top left picture, it's like fluffy. So we shouldn't be leveling the material. We should be leaving the material as aerated as possible on the wall, because that's gonna optimize its thermal performance as well as its porosity, which means that the moisture movement is going to be even more effective. So this can be applied in layers up to 120 millimeter layers. Overall thickness, which means that you can even reach enerfit levels with diaphanite. It's a comprehensive system. So for different detailing, there are different variations of the materials for the bottom of the wall, for some junctions. So it's a full system that can be detailed properly, and that's a complete solution. Now, other than that, this should always be finished with a thin lime plaster. You can use the lime plaster of the system. It's called Argasem, but there are also it's the potential to use other sorts of finishes like clay finish or other lime plasters over the top of that. So that's a standard that works as a standalone system for leveling the wall as well as insulating the wall. Now you can use diaphanite in combination with other systems. So secondly, here you can see the wood fiber insulation and the calcium silicate insulation, the calcitherm. So these are board systems, insulating systems. These are again hygroscopic natural insulation systems that come in the form of board. You can level the wall with diaphanite, and then you can top up either with the wood fiber board or with a calcium silicate board. Now, the process is very easy, because it's like, as long as you have a perfectly level wall with diaphanite, then you can go ahead and just tile the wall with these boarded systems. Now, why should you use wood fiber over calcium silicate board or the other way around. Wood fiber is hygroscopic and can deal with a certain amount of moisture, cannot deal with huge amount of moisture. So if your wall is unrendered, for example, on the outside, or if it's a very exposed orientation, or if it's a basement, or if you have like huge amount of rising damp issues, then wood fiber would not be the best case scenario. In this case, calcium silicate board, which even more than diaphanite is capillary active, so it's the most capillary active of all these three systems. Actually, calcium silicate board can hold 5 times its weight in water. So it's very, very absorptive without changing its without swelling or changing its consistency as material. So when you have very wet situations, very extreme moisture situations, you can use diaphanite in combination with the calcium silicate board, with the calcitherm. So that's the main difference between those two boards. Now, with all these systems, the lambda values on the thermal conductivity of these systems vary from 0.037, which is the best, and I refer to diaphanite, to 0.059, which is the calcium silicate board. So with 50 or 60 millimeters of any of these materials, you can improve the U value of the wall by around 4 times. So if the wall has a U value of around 2, with 50, 60 millimeters, you can go down to 0.6 or even lower, maybe 0.5. So just to give you an indication of the thickness you need. And by doing that, by going that low in terms of the U value, you get a huge improvement in thermal comfort. Of course, you can go lower if you want, and there are other risks incorporated in that. But if you go up to that level, then you can make sure that you definitely have significantly improved the thermal comfort in your house. What's important, though, again, is that you should, if possible, include all the detailing and in your insulation, and make sure the insulation is as continuous as possible, including intermediate floor junctions, window reveals, shutter boxes, and so on. So that was for the walls. Now for the floors, again, James talked about the glass foam and that sort of floor solutions. Now, if you have a solid wall, a solid floor like a slab, then you can add some diaphanite screed insulation on the top. So diaphanite comes in the form of screed too. So you can just pour the diaphanite lime cork screed on the top of a solid slab, or you could use that even on the top of glass foam aggregates. So again, dual use here for diaphanite, and that's for solid floors. Now, if you have a timber floor, that's a little bit more tricky because you have to take care of the airtightness, because air leakages from the floors of that type is a huge pain, and the owners always complain about cold feet and air leakages through that. So we have developed a system where we use 2 sorts of membranes: a breather membrane, the Solitex Plus, one of the Proclima range. This membrane could be draped in between the joists if you're working from above, because usually the crawl space is inaccessible. So that's the most common application. Drape the membrane from above, the blue membrane, then fulfill with fibrous insulation, either wood fiber flexible mats or hemp jute insulation in between. Fulfill the gaps, and then on the top of that you can put a green membrane, which is a vapor control membrane, fully sealed on the overlaps and the perimeter, and then we have a fully enclosed insulation, optimized performance, and fully sealed floor all around, and that's gonna significantly again improve the performance of the floor. And now for the wall, for the roofs, yeah, we supply again same range of products. It's the Gotex wood fiber in the more rigid or more flexible form, either for in between rafter insulation, and the more rigid form for either over the top of the rafters insulation, or under the rafters insulation can be fixed into the rafters. And also for the ceilings, when you have a ceiling insulation at the ceiling level, you can use again both these types of insulation, either in between the joists or above. What's also important in the ceiling levels insulation is that you should be taking care of the airtightness 100%, because especially when you have a cold attic, vapor from the rooms below can pass through the insulation and gaps and cracks, and you may have a huge amount of condensation on the cold timber in the cold attic, and that's gonna eventually become mold and degrade the timber. So tightness is important in this case too. I think that's all very quickly. Sorry, I was a little bit yeah, nervous because we're a little bit late, but hopefully I've covered some of it.
Don't worry, Ilias, that's been wonderful. Thank you very much. That was a brilliant whistle through and tied in very nicely with the things that James talked about as well. So thank you for that. So yes, if your question hasn't been answered, as I say, hopefully you'll be able to get back in touch with Chris or James or Ilias or Penny, or get in touch with CAFS. We have got some more webinars coming up, so it may be that we're talking on similar subjects where you might be able to get your questions answered there. Look out for our Appleby webinar on the Appleby Moot Hall tomorrow, and then there's another webinar next week, and we've got a whole series of webinars on low energy retrofitting homes. As I mentioned before, if you want a short advice call with one of our CAFS Energy advisors, they're free, give us a call. Or if you're thinking of a retrofit and you want to start with a free consultation phone call, again, get in touch with us. And we can also provide a quote for a full energy advice audit as well. So those are the contact details for CAFS, if that's going to be providing information that would help you. We've got these other webinars, so do look out for all of those. They're all on our website there, and they're all free, so go for it. So thank you so much for coming along to the webinar. Thank you for some really good questions to keep us on our toes, and thank you very much to the panel for your presentations and for giving us a really great sense of what can be done with a traditional building, and that we can really turn it into a warm and comfortable home, which is really what we all want at the end of the day. So thank you very much to all of you, and I hope to see you again at another webinar soon.